So our next talk will be delivered by Professor Ronghui Xu. Professor Xu is from University of California, San Diego, and she has been working in the causal inference field for years. And she is also directing the biostatistics unit at UCSD Clinical and Translational Research Institute that is partially funded by an NIH grant. She is also the lead statistician at the Organization of Teratology Information Specialist Collaborative Research Center. And I'm sure that she will share a lot of very interesting topic with us. And today, specifically, she will talk about doubly robust inference, especially for the survival analysis. Okay, so Professor Xu, welcome.
Okay, so nice talks, the first three speakers. So I'm going to talk about something just slightly more in depth, because I've been working in the field of survival analysis since my PhD long time ago. So this is joint work with a team of students, former students, and current faculty at UC San Diego. Okay, yeah, okay, there we go. Mm-hmm. It works. All right. So I don't have to go into details. Everybody in this audience know what the potential outcomes are. We're considering two treatments. So for survival outcome T, there's typically also censoring time. And then for each of the potential outcome, you have the possibly censored time X, and then the event indicator delta. So because we're under this kind of framework, so a contrast between the two versions of potential outcome would define a causal estimate. So as I know, Ross himself was giving the opening talk for this conference, which is exactly the paper we're citing here. This is to acknowledge that there's currently ongoing debate, which we also contributed a little bit to complement Ross' nice paper, that whether hazard is a good quantity to use to quantify treatment effect. But for today's talk, I'm going to talk about the hazard function, and that is the one that gives the Cox model. So under two treatment options, a totally general model, and that's like model in quotes because this is saturated. So if I call beta T as the log hazard ratio between the two potential outcomes under A equal to 1 versus 0, this is not really imposing any assumption. The Cox model, on the other hand, would impose that this log hazard ratio to be constant. So as a special case, we would have the marginal structural Cox model as proposed over 2 decades ago. And this has been, despite the debate on hazard function, has been widely used in all sorts of applied studies. So these are the local studies I'm involved with in different disease areas. Now, since we're considering the more general model where beta is allowed to change over time, instead of estimating beta as a function of time, perhaps, and this is also being noted from a couple of decades ago during my PhD thesis work, up across 2 decades now, people have been talking about, okay, if you want to relax the proportional hazards assumption, then perhaps you want to estimate some kind of time averaged treatment effect. So if you think of this omega as any positive weight, then this is the general formula for an average treatment effect. Now, obviously, if the Cox model actually holds, then this average is the log hazard ratio under the Cox model. Okay. So before I talk about what exactly the average is, to motivate, we want to actually think about the causal problem here, where we are missing the counterfactual outcome, of course, but also because in survival analysis, due to loss to follow-up and other reasons, we typically have right censoring. Now, the weakest assumption we can have here is the kind of informative censoring, meaning that the censoring could depend on some variables that are not in the model. Remember, our model only has treatment A in it because it's a marginal structural model. So if we allow censoring to actually depend on some covariates that are observed, then that should be sufficient to identify the treatment and the T distribution, basically. Okay, so this is just to mention informative censoring has got a lot of attention in the last couple of years in clinical oncology. For example, we did a review before I gave a talk last year at Memorial Sloan Kettering. So very quickly, the assumptions that we make are the typical causal inference, SUTVA, consistency, no unmeasured confounding. So note that I use the same set of covariate Z to denote the confounders, as well as I mentioned earlier, the Z that induced the informative censoring. And in addition, because we are going to look at double robust approaches, so we are going to assume all the probabilities are bounded away from zero, the probabilities that will be eventually on the denominator. So that's sometimes called the overlap assumption. Okay, so we use the full data approach as described in Teate's book. That's a very clear graduate textbook, really. So the full data is very simple. If I get to observe both versions of the potential outcome of my event time, as well as the covariate Z, that's it. That's everything I would want. Now, in reality, what we observe are the treatment assignment A, as well as the censored outcomes, the X and delta. Okay, so with the full data, which I should know how to estimate the treatment effect, I'm going to denote these counting processes that are commonly used for the full data, as well as the at-risk process. And with that, I can mimic the martingale, although we have to be a little careful. If the true model, the beta changes over time, and we impose a constant beta here, then this quantity, what I call M, is in fact not a martingale. On the other hand, if the Cox model actually holds, meaning beta, the beta T is a constant beta, then you do have a full data martingale with respect to the relevant filtration. So this motivates the estimating function that's going to eventually define my estimate. What we do is, depends on how familiar people are with survival analysis and the Cox model. This is actually one way of writing down the typical Cox model estimator by looking at the increment of the martingale, which should be mean zero, as well as this is another equation. This is like the least squares equation for intercept, and this is for the slope. So I have little a times the martingale integrated out. Once again, these are commonly used quantities under the Cox model that if we have just ID observed data, these will give the partial likelihood estimator and the Bradlow's estimate of the baseline hazard, etc. So that introduces the full data estimating functions here. Now, if we allow the saturated beta T model, what we could show is the following, that solving the two full data estimating equations I had on the last slide is going to give us the solution beta star as defined by this estimating function. So don't worry about what exactly is in here. It is some kind of, I'll explain more on the next couple of slides. This is almost like some kind of expectation quantity under the true beta T versus under the forced constant beta star integrated out to be zero. And then we also have an equation expression for the baseline, basically all the least false baseline hazard. So the important thing for the moment is obviously if the beta t is a constant, then you are estimating the beta under the Cox model, and the lambda star will give you the cumulative baseline hazard. And here's some illustration that if you have just arbitrarily two different hazard functions, you can plot their log hazard ratio, just divide, take log. They could be different shape. And this is numerically what the beta star, the average is. That's the red dotted line. To make it slightly more solid, and this again, we knew it from over 2 decades ago, if we have randomization, let's say 1-to-1, then we are no longer in the potential outcome world. Then what you have, these expectations I mentioned before, is in fact the probability of treatment assignment given survival time. The expectation under the true beta t and the expectation under this beta star, this average effect. So with that, you can do a quick Taylor expansion, and you can see the weight function to give this beta star, in fact, is some quantity that is actually the variance of A given T, which we know changes quite mildly over time, times the density of the marginal distribution of T. So this gives some physical meaning to what kind of average treatment effect we are looking at. Average that's over time. Okay, I'm going to skip to say there are special cases we understand very well what this beta star is, such as under the Giro family of transformation models. I'm going to talk about how to actually estimate using the observed data. So again, now we have the observed counting process, and we have the observed at risk process. And again, we mimic the martingale definition to form this M quantity, which is now definitely not a martingale if we have confounding and if we have informative sensory. Okay, but we have this M quantity. And what we can do at first step is use inverse probability weighting. If we know the propensity score for treatment and we know the sensory distribution given the treatment and the covariates. So these are the IPW version of the full data estimating equation that I showed you before. And the one can show that they indeed would identify the beta star and the lambda star that I defined earlier in the first lemma. And then, of course, we are not going to be satisfied with just using IPW because the model could be wrong. And then if machine learning approaches are used, IPW itself does not give root n consistent inference. So luckily in this case, in order to augment these two types of weights, it actually has been done in some very simple cases by Robbins and co-authors. And so these are two thesis work to extend to the Cox model, where the augmentation takes form of these conditional expectations that I'm not going to go through in detail. But what you will see at the end are these AIPW estimating functions that, again, for people, if anybody in the audience happen to be familiar with the Cox model, they are augmented version of the Cox model equations, where this is normally what you have under the Cox model, just A times the counting process, but with augmentation. And again, here's the A times at risk process, e to the beta A, again with augmentation. Okay, so with that, the first result is the double robustness, which says among two sets of nuisance functions, one is the conditional survival function of my event time given A and Z. The other two are the missing data mechanisms, that's the propensity score and the sensory distribution. If either of the two are true nuisance parameters, then the two AIPW equations would identify the beta star and lambda star that I want. Okay, so this will give then the familiar model double robustness if root n consistent estimators are used, or the rate double robustness as previous speakers talked about. So you can have machine learning methods with a product rate that I'll show later. And this is extremely important here because the Cox model is a highly nonlinear model, and there's so-called non-collapsibility, meaning if we start with the Cox MSM that define your causal estimate, so if you assume the Cox model, then it is basically impossible to specify a parametric or semi-parametric model that does not contradict with the original Cox model. So this was known a while back as well. So that means non-parametric or machine learning method must be used if we actually want to make use of the double robust approach. Okay, so I'm going to skip the cross-fitting algorithm. It's a bit non-trivial with the Cox model. I'm going to show the rate condition, which is a bit more complicated than some of the previous talks because we have two nuisance functions, both are of t. So in addition to these product norms that are familiar, we have all these cross-product terms that are integrals. Okay, so you have the nuisance S function, compare its choose, the nuisance SC function, compare with its choose. So the technical detail is a bit more complicated as always for the survival models. But nonetheless, if you have these conditions satisfied little o n to the half, then we have the inference function for the estimator. And let me show some simulation results. I'm going to only briefly show you the two scenarios. One is where the, this is under the Cox model, I should mention. So there is a true beta that's -1 and the cumulative baseline that's t, basically that's exponential. And then the two missing data models are the nice Cox and the logistic regression as the really nice scenario, or the last one I'm going to show is something very far from any of these parametric models. And here are the results. So first of all, notice, as I mentioned, under the Cox MSM, the conditional T model, if you are using a parametric one, such as another Cox model, so you start with a Cox model given only A, and then you use another Cox model given A and Z, this model is pretty much guaranteed to be wrong. So anything in red is a wrong model. But because of double robustness, even though this is in red, I have the rest that are nice and black, then everything is working fine. My coverage is good, bias is good, etc. Even IPW in this case worked okay. By the way, I should specify that this is random survival forest, and TWAN is a boosting package for fitting propensity score models. People probably know here. IPW are also not too bad, although as I mentioned, with these machine learning methods, there's really no theoretical guarantee for root n inference. The naive Cox model, of course, is way off. Compared to the more difficult scenario, okay, so remember here, the C and the propensity score models are highly non-parametric. So everything is very wrong here. The only thing that is in black are this last one. And you can see this last one in the first section is the only one that has the correct coverage. Okay, and the reason is in the rate double robustness, I didn't mention earlier. This is where you need both models, both sets of models to be consistent, and then with that product rate that's faster than root n. So anything that's wrong is not under the theoretical guarantee we have. And meanwhile, you can see the IPW estimators here are not so satisfactory. This is kind of a show of the performance of the double robust estimator with machine learners in both sets of nuisance. And then finally, I have a relatively simple data set, but that's the study that funded our work partially. So this is exposure midlife drinking for a cohort that's in Hawaii, Honolulu, among Japanese men actually. So there's a long follow-up. And then we are looking at the outcome that's called impairment-free survival. So this is later on a dementia study starting from the 1990s. It's an aging study. We have some loss to follow-up due to censoring. And we have some covariates that are collected in the data set. And here are the different estimators. So first of all, you can see the naive Cox estimate is quite relatively large. Then you have the IPW estimators using different nuisance estimates. And then you have different augmented IPW estimators, as I mentioned before, using parametric, semi-parametric, or machine learners. So this is, of course, real data. We don't know what the truth is, and we don't even know the Cox model holds. So the interpretation here that I can mention is if one does not believe the Cox model hold, then what we are looking at is the time averaged log hazard ratio estimates as we defined earlier. So that's pretty much it. And these are some of the work we've done that are on archive.
Thank you, Professor Xu. That is very, very interesting topics. Then I want to ask the audience whether we have any questions. Feel free to unmute yourself to ask questions. So Professor Xu, since you mentioned about, informative censoring, in general, like what is your general comment when we apply survival analysis in general? Like what will be, because most of the situation I have met with, although we assume non-informative censoring, but most of the case, actually there is some informative censoring there.
Yeah, so the thing to be careful is what's included in the model. So if we are just using Kaplan-Meier estimator, you're not including anything. So you are assuming censoring to be completely independent of the survival time, right? And that's a very strong assumption because sometimes, within different treatment groups, the, censoring could depend on treatment. So that was the literature review also emphasized. So it depends on what's in the model. And do you have things that are not in the model that might be affecting censoring?
Right, yeah. So, I mean, it's also non-testable. So do you do a lot of sensitivity analysis in the real data application? Do your collaborators, they buy that?
Yeah, I like your thinking. In reality, we have not, but I know there are people in pharmaceutical industry. I mean, they're quite a group pushing for this kind of, be more careful. Yeah.
Thank you so much. I just want to, know a little bit more about it because you are so experienced. Thank you so much for sharing those experiences.
Thank you.